Hello, welcome, ninth period discrete math. Welcome, juniors who are not here because of AP Lit, Lang.
Also macro right now.
Some might be taking macro, others are just not here. Also, for my many fans from all around the world, this is a great day. We are going to be learning about Polyhedra. And we have been learning about Polyhedra, but we're going to be learning like more about Polyhedra, man. It's actually like awesome. This is something I did not know 30 hours ago. I did not know was possible, and now that it's possible, it's like the greatest thing.
You should like sit up and teach us.
No, it's easy, and that's the thing about Polyhedra. Anyone can do it because it's not that hard, but it's fun. Shall we begin, PG? First, I am not assuming that you know like any geometry because this is America, and they don't teach geometry anymore. So let's do some remedial geometry. I even called it Remedial Geometry background page. What's up? I taught you some geometry. Good, let's begin. Take a pentagon. It need not be a regular pentagon. I'm going to present this in the order that you have probably seen it presented to you in a geometry class in a public school. What is the sum of the interior angles in this pentagon? How does one go about doing that?
Split it into 3 triangles.
Yeah, you use the fact that, can I get a green marker from the box? You use the fact that a triangle has 180 degrees, and what we can do is we can split up this pentagon into triangles, thank you. And so we can just kind of go like, yeah, and yeah. Right. Having done that, observe that, this angle and this angle were like angles of the original pentagon, but then some of the angles of the original pentagon got like split up. These don't mean congruent, they just mean I'm drawing an angle. And then like this got split up into like 3, and then like et cetera, right? Okay, so if I were to add up all these marked angles, then I would get back exactly all the interior angles of the pentagon. Yeah. Woo! Good. So, how many angles are in this triangle? Well, 180, 180, and 180, yeah? Therefore, how many total angles are there in the pentagon? 540. 180 times 3 is 540. Good. Alright, now, I was too lazy to draw like a generic n-gon, so please treat this next n-gon as a generic n-gon. So, like it has some number of sides. This is what your packet looks like in my imagination. How can we figure out the total interior angle sum for this n-gon? We can partition it up into triangles. How many triangles? Yeah, it's like actually like a thing, right? Pick a particular vertex, and then it's like a counting problem, right? How many other vertices are there, which if I draw the segment connecting this vertex to that vertex will be like a diagonal, like n minus 2 of them, right? Because the 2 adjacent ones like don't count. So I draw n minus 2 lines, and each of those lines makes... What?
Draw n minus 3 lines.
N minus 3, you are right. Good. Yeah, so like if there are n vertices, then there's that vertex, and then there are these 2 vertices, so those don't count. But for the other n minus 3 vertices, yeah, this is some good stuff. It's better to be like right and everything. So now this thing I just said is better. There are, Sure. N minus 3 other vertices, and each of those other vertices will be a diagonal, and thus leaving me with n minus 2 triangles. Agreed? Say agreed. Woo! Alright, so the sum of the interior angles in any polygon is 180 times n minus 2, where the polygon has n sides. This is pretty much exactly how you learned this once upon a time, if you remember.
I do not remember.
You have just no memory of this? Had you totally forgotten this formula also? Just curious now.
I mean, like it goes back to like I took geometry so too long ago.
Good. All right, good thing you're here. All right, next. Well, in addition to interior angles, we also have exterior angles. All right, there's like a lot to say about this. So what is an exterior angle? It's a little bit difficult to define precisely, and I don't really care to do so. But it's what you get when you like extend a side, but you know, from the vertex. So like boom, like that's an exterior angle, and like so is this one, and this one, and this one, and this one. Notice how I did all these like in the same direction, so to speak. All right, well, what can I say about these exterior angles? They add to 360. Well, that's just kind of like remembers that or something. How do I know?
Well, say that you're just chilling at the top of that Pentagon, and you're walking around it.
Oh, he's giving the intuitive proof. Okay, wait, let's give the tedious proof, which is often the one typically done. Then we'll come back to that's for like the deep proof. So the tedious proof is to be like, I want to know what happens when I add up this guy, this guy, this guy, this guy, and this guy. What is one way to think about these exterior angles? Yeah, William.
Like 180 minus each of the interior.
Yeah, each of these exterior angles has like a corresponding interior angle, which it is like supplementary with, yeah? Okay, and so if I like add up all the red interior angles, and I add to that all the exterior angles, then what do I get? Like a bunch of 180s. How many 180s? Let's do it in N. Yeah, then I get 180N, yeah? Okay, but then I already know, because we just talked about it, that the sum of the reds is 180N minus 2. So if this is 180N minus 2 plus the sum of the blues is like 180N, this is like maybe slightly too remedial, then what is the sum of the blues? The sum of the blues is just 360, so fact. Alright, so I have just proven, I think, in general, using Williams' argument, that assuming you already know the formula for the sum of the interior angles, which we do, then the sum of the exterior angles is 360 for any polygon. Alright, so that's kind of like deep and cool. This is such a interesting and important theorem. It gets like, I don't think it gets enough attention. So let's explore a couple of other alternative proofs of this fact. Well, that's.
So if you start at the top of the Pentagon and then you walk around it, say to the right, then every single time you turn a corner, the degree by which you're turning is the thing marked in blue. And then by the time you get back up to the top of the Pentagon, you're going to have turned exactly once.
Yeah, let's actually, do you mind if I slightly amend your story to start like, let's say I start actually like here. Then I get to do a turn first,
Yeah.
right? So if I'm here, if I'm here, and let's say I'm also like in a car and stuff, or I don't know, it doesn't matter. If I'm here, then it's kind of like I'm here and I turn by a certain amount, right? So I perform a turn. And now I like go this way, and then I get here, and now I also like turn. And then I go this way, and then I'm here, and then I turn, and then I'm here, then I go this way, and then I turn, and I go here, and then I turn, and then I walk back to where I started. Well, just intuitively speaking, like what I've done is really like a sequence of like translations and rotations, right? Sort of, so to speak, right? Starting here, I sort of went forward, turned, went forward, turned, went forward, turned, forward, turned, forward, turned, forward. And I'm back exactly where I started, and crucially pointing in the same direction as I was starting in. And so I must have turned 360 degrees. Cool? Anyone want to say that slightly better? I feel like that's pretty good. Yeah. And so there was nothing particular about this being a pentagon, right? Any just like full like loop around a polygon must have 360 degrees. And also the nice thing is there's nothing the only thing I cared about was the rotations. So another way to sort of see this is to think about the vector translations as being very, very small. Do you see a tiny, tiny, tiny little n-gon on the bottom right-hand corner of your page, also known as the middle of the page?
I see a tiny pentagon.
Yeah, good. I see a tiny n-gon. So if I want to know the sum of the exterior angles of this, well now like it sort of becomes like more intuitively clear, I think, if you shrink the angles, that this is 360, because maybe like I didn't even shrink it enough. Did I do something wrong? If you shrink it like to like a point, man, there's a very, very tiny n-gon right there. Well then, like, you know, then you sort of have It's terrible. Good, good, get it? All right.
We get it.
Fact: sum of the exterior angles in any polygon is 360. This is great because it's also like a much better way if you're talking about like regular polygons only. Like suppose I have a dodecagon, a 12-sided polygon. Well, suppose one wants the interior angle of a dodecagon. Well, what's one way to do this? Yeah, the good way, the lame way to do this would be to find the sum of all of the interior angles of a dodecagon, then divide by 12. That would work fine. But maybe it's like simpler and clearer to just, if you just feel in deep in your heart this exterior angle theorem, then this exterior angle is 30. I over 2. Wait, the exterior angle of a dodecagon, which has 12 sides, 360 over 12, so that's 30, boom. And we're just mixing degrees and radians as we feel like. Good, so then that's 150 boomed up. Alright, so that's how you like to do that fast. Alright, okay, cool, say cool. I have a couple more small things to say. I have like sort of like another maybe way of thinking about these exterior. So another way of talking about these exterior angles, it's like, okay, how big can an angle of a polygon be at most? Like a normal chill polygon, non-convex. No, convex. Convex. Yeah, if I have a convex polygon, how big can the angle be? Like 179, like plus epsilon, or yeah, right, or like 180 minus epsilon. So yeah, so like 180 is like the max, and you can be 180, like exclusive, right? So if any particular angle has to be something less than 180, then the exterior angle theorem kind of says, like, dude, take any polygon. You only have like 180, you only have 360 degrees of like not being as big as you can be to go around, right? Any angle can be only so small, because if you have every time in any one of these interior angles of this polygon, like think of the exterior angle as like the amount that you wasted or whatever, right? You only have a total of 360 degrees of like wasting going on that you can do for that entire polygon. All right. And you can just imagine a polygon with like a million sides, right? All the exterior angles are going to be like, you know, small. Very, very, very small. Okay. You can even think about this even more loosely as, like, imagine I have a line. So now, imagine I have, again I have an n-gon. I can just draw arbitrary lines through these vertices. And I think, if I've done this correctly, I think that the sum of all of these angles that are like left over has to be 360 as well. Is that obvious? I feel like it's not totally obvious. Should like draw some lines. Read.
Yeah, you
Yeah, so if I draw the actual ones now like out, and I get it down, and I get it down, and I get it down, then like, right, this was the, I know that the reds all add up to 360, right? And they're like vertical angles, exactly, right? So this is equal to to this, and like, etc. Cool? I think this is like, oh, that's like even another cool way of doing it. But alright, so anyway, good. Let me just finish drawing this green. So yeah, since the greens are all equal to each other by vertical angles, then by sort of letting there be like a line in each vertex and tilting it slightly, we see that like the two angles formed is the same as a vertical angle. Okay, so I really feel that like you have what this sort of theorem deeply says, I think, to me, is we have 360 degrees of like not being 180 to go around for your whole polygon. Cool?
Oh, wait, no, maybe he's right.
Good? Now, to 3D, we go. Dun 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 dun. What is the analogous fact about polyhedra? Oh, this man is intrigued. Here's a polyhedron. This
so intrigued.
is a cube octahedron. Also, I'm wearing my cube octahedron t-shirt. Thank you for complimenting me on that, each one of you, before the video started.
He's wearing a t-shirt.
What can I say about the vertices of a polyhedron? So I have all these little angles. It's difficult to find the exact language to describe all these little angles, but these are like, if I'm at a particular vertex, and I add up all the angles on all the faces meeting at that vertex, all the angles on all the faces, if I sum up all the angles of the faces whose vertex of that angle is the vertex of the polyhedron, everyone knows what I'm talking about. These four little angles, man.
Oh yeah, that sounds super intuitive.
These four little angles, then they of course have to be less than 360. Someone's cooperating, right? Yeah, they have to be less than 360, because if they were equal to 360, then it would just be flat. We talked about this already when we gave the loose proof of the fact that there are only 5 platonic solids. Okay, well, I can calculate how much less than 360 they are. Whoa. And there's a name for that. It is called the angular defect. All right, what is the angular defect for a cube octahedron?
6.
He is doing math in his head. He is right. Notice, Wilbass says that an equilateral triangle is 60 degrees, 90, 90. So if you add up 90 and 90 and 60 and 60, you have only like 60 left over, yeah? Okay, so incredible fact, which I learned last year, but I didn't like understand it or process it or really appreciate how useful it is that the sum of the angular defects for any polyhedron is 720. Whoa.
Why is that useful?
There are only, you'll see in a minute, there are only 720 total degrees to go around that you're allowed to waste, is the way I like to think of it, right? If at every vertex you're wasting some, the amount by which you're less than 50. All right, good. The proof of it, next page, is, or maybe you're already on that page, is like super straightforward. And you kind of think like, man, why does not every kid in America learn this? Because it's so simple. And in fact, it's even a little bit deeper than, can you move the camera, just pick it up and move it over there, it's like better.
Steven, the
Or
camera
not.
loves you.
Or not.
Oh.
Alright, theorem, what does it say on your worksheet? On your worksheet it says something like, yo, the angular defect at a vertex of a polyhedron is the amount by which the sum of the face angles meeting at that vertex falls short of 2 pi. I'm switching back to radians now just because I feel like it. And the total angular defect, which I'm calling t, is the sum of the angular defect. So theorem, t, the total angular defect for all the vertices of any polyhedron is 2 pi times v minus e plus f. And so we're seeing actually now that saying it's 720 is not quite correct. It's 4 pi if this is 2. And this is 2 for a shape with Euler characteristic 2, which is like all the so-called spherical polyhedra. Follow? Okay, good. All right, let's prove this. Woo, we do it. So we begin. What is t just like, I'll begin. What is t just like by definition? Say sum of the angular defects.
The sum of the angular defects.
Good, so it is the sum over like all the vertices of the angular defect, I'll just say at vertex v sub I. Good to good. Okay, next, please guys tell me what the angular defect actually is by definition.
360 minus the sum of all the things.
Angles. Good. Yeah, that's right. But I converted back now to like radians. So this is going to be 2 pi minus the sum of the angles on the faces which are at vertex v sub I. Good enough? Say good enough. Okay, now I'll split up this sum by dividing through. So if I split up this sum by dividing through, I get the sum of, well, this is sort of saying like add up through all the vertices, 2 pi every single time. Well, if I add 2 pi, if I add 2 pi for every single vertex, then what do I get? 2 pi plus 2 pi plus 2 pi plus 2 pi, and I keep adding 2 pi every time there's a vertex. So I end up with 2 pi v, where v is the number of vertices. Cool? And then minus, continuing to distribute the sigma. Now I'm still summing through all the vertices, and it's just the same thing again, right? The sum of the angles on faces at vertex vi. Okay, good. Well, now I can sort of just reorganize all of these angles, because what I'm really doing now is I'm going through vertex by vertex, and I'm looking at a particular vertex, and I'm looking at all the angles that meet at that vertex, right? But by doing this, summing through all the vertices, I'm just counting every angle on every face of the polyhedron. Agree? Yeah. So if I'm counting every angle on every face of the polyhedron, let's count the angles face by face instead. Aha! So now I'm going to take the sum of all the faces, and I'm going to put I'm going to look at each face, and I'm going to take the sum of the angles on that particular face. Pretty clear, I think, right? Say right. All right. Good. So then we get 2 pi v minus. All right, well, how many angles are there on a given face? Or rather, take a particular face. What do I know about the sums of the angles on that face? It's based on the number of sides of that face. So again, if I sum through each face, it's simply 180 times,
That should be pi, right?
oh, I guess pi, yep, thank you. Pi times n minus 2, where n is like the number of, so I'll just write like number of edges on face f sub I minus 2. That's what we did in the remedial geometry warm-up. Good, good? And all of this is like in this sigma. Okay, well, this can be, again, split up into, I'm now taking the sum of a bunch of, well, yeah, let's just like split them up, right? So I'm taking what? Oh yeah. So this becomes pi times the sum through each of the faces of the number of edges on face f sub I. But then like minus becomes like plus and that pi is times that 2, right? So I have 2 pi. How many of these 2 pi's do I have? 1 for every face. Is everyone okay with that? I'm kind of like going a little, skipping a little bit about it, right? But I'm summing for every single face. I have a pi times a 2. It's being subtracted, but it's being double subtracted. All right, and finally, what happens if I go through every face and count the number of edges on that face? One face at a time, counting all the edges, adding them all up. By handshake, I've counted every edge twice. Yeah? Okay, so if I've counted every edge twice, then this gives me 2 pi v minus pi 2e plus 2 pi f. Whoa. Whoa. Good. Yeah. So it's like, do you agree? It's like kind of like easy-ish, right? It's just like it's nothing deep. The proof isn't deep. It's just says it just like kind of works. Or maybe there's a deeper interpretation, but I don't know. All right. So this is amazing. It says if you just go all around any polyhedron, by the way, at no point did I use like regularity in any kind of way. Then you don't need to turn it. Well, you can. Well, whatever. I'm going back over here. Then I will always get that all of these add up to 4 pi. And then what's cool is on like a torus, or a toroid, I should say, as we have seen, this has Euler characteristic 0, right? Did we talk about why?
Yeah.
I think I started to like right at the end of class, right? Because you kind of take these 2 faces and you glue the faces together and you...
We did at the end of class, then we did the next class.
Yeah.
Also, okay, good. So since this has Euler character 0, what is the sum of the angular defect for this whole polyhedron? 0, right? And that's because the angles on the inside have actually like negative angular defect, because these add up to more than 360, right? And so you have 360 minus things. All right, and this is related to like curvature and stuff in ways that I don't understand. But it's like topology. All right, good. What can I use this for? So I knew all this already, but I didn't know the proof. But what I did not realize, mind blown, next page, is that this can be used in a very easy, smooth manner to calculate all of the vertices, edges, and faces of any shape if I know what it locally looks like. Okay, take our friend, the truncated cube octahedron, for example. Hi. Which is the truncated cube octahedron?
Which one is the truncated cube octahedron?
That is the cube octahedron. Stop, hold the cube octahedron up in frame. That's the cube octahedron. What happens if you truncate it? Every square becomes a octagon, every vertex becomes a square, and every triangle becomes a hexagon, yeah? This one, boom. This is the truncated cube octahedron. Now, an amateur might take this truncated cube octahedron and like try to count the vertices, edges, and faces. And if you guys remember, I told you when the 7th grade girls were trying to do this at FIST, they would just like start counting, and then they would get like halfway around. They would be like, "Where did I start? Where was my thumb?" And it just became really hard. Now, if you're smart and like organized, you could probably not screw up by like looking at it and sort of like trying to do it all at once. But that's like lame. Imagine instead you're like a bug on a vertex. This solid being Archimedean means that it's like perfectly symmetrical. I claim that the only thing you need to tell me everything there is to know about this Archimedean solid is what's going on at a single vertex, plus like facts about polyhedra. Okay, what is going on at a single vertex of the Archimedean solid? Say hexagon, square, octagon. Hexagon, square, octagon. Good. So this Archimedean solid is associated with it's like hexagon, square, octagon. Good. From this alone, I claim that we can quickly tell how many vertices there are. Ready? Say ready.
Ready.
Good, let's do it. Okay, well it's a kind of a counting argument, right? Let there be like h hexagons and s squares and okay, O is weird, so let's like go to like some other like thingy. Because it doesn't look like 0, O, octagons. All right, well, what are some simple facts about H, S, and O? Actually, maybe we can just figure out how many vertices there are like first, like really fast.
Yeah.
That's like more impressive. Let's do that. How many vertices are there? Well, simply calculate the angular defect at a single vertex. So what's the interior angle of an octagon?
135.
Good. So these people who are paying attention and whatever, or like knew stuff already, probably went through the following logic. It's an octagon, so it has 8 exterior angles. It's regular, so they're all the same. So each one of these exterior angles is 45, because like 360 divided by 8, yeah? And then this is like therefore 135. Woo woo! So 130, each octagon contributes 135 degrees, each square contributes 90, and each hexagon contributes 120. So the sum of all these is?
345.
That's right, 345. So what is the angular defect at any given vertex? 15 degrees. Woo! If the angular defect is 15 degrees, then what is T, the total angular defect for the entire polyhedron?
720.
It is 720. It is also 15 degrees per vertex, like times the number of vertices. I'm teaching this like kind of in a boring way, so it's like you guys aren't pumped. I'm sorry. Should I go like faster? It's cool. I think it's pretty cool. It's like mind blowing. To me, this is when Siddharth showed me this yesterday, it like blew my mind. It's like, oh my god. All I need to do is know what's going on at one single vertex.
It's
It's
I
cool.
see it's really practically useful. I don't think
Boom.
it's
345. Angular defect 15. How many vertices on a truncated cube octahedron? I don't know. But I know that there's 15 and it must add up to 4 pi. So therefore V is
48.
48. Woo! There are 48 vertices on a truncated cube octahedron. Good. Let's figure out the other thing. So that's 1 down, 2 to go. Let's count all the faces, right? If I add up the number of hexagons and the number of octagons and the number of squares, then what do I get? The number of faces. Thank you. Good. How about vertices? Let's count the vertices. Well, go through every hexagon. How many vertices on every hexagon? 6. How many vertices on every octagon? 8. How many vertices on every square? 4. Okay, now, what have I actually just done? Pause for some wait time. What have I actually just done with respect to counting vertices? Prem. Prem says I have triple counted every vertex. Does everyone agree? I have triple counted every vertex because by counting the vertex once for each square and once for each octagon and once for each hexagon, well, every vertex is on an octagon, a hexagon, and a square. So that's like pretty cool. Okay, now let's do the same thing with edges. Well, there are, if I'm counting edges, there are 6 edges on every hexagon, 8 edges on every octagon, 4 edges on every square. But now what have I done with respect to edge counting?
Double.
Yeah, wait, is this hard?